Good day everyone and welcome to our next experiment. In this video, we will be demonstrating how do we determine the molecular weight of a volatile liquid. So let's begin with some background. For a quick review, the molecular weight of a compound is the sum of the atomic masses of all its elements. We hope that you still know how to determine the molecular weight of a compound if you know the identity of the compound. However, how do you determine the molecular weight of a compound if you don't know what its identity? You don't know what type of compound it is, and you don't know its elemental composition. So one of the earliest experimental techniques to determine the molecular weight of an unknown volatile solid is called the Dumas method, and this is what we will be demonstrating today. The Dumas method is heavily reliant on the ideal gas law to calculate the number of moles of a vapor trapped in a flask at a certain temperature and pressure. To refresh you, the ideal gas law is this equation here that's defined as PV equals nRT, wherein P is the pressure, V is the volume, N is the number of moles of the gas, R is the universal gas constant. Now, we have several values for the universal gas constant, but here are the most commonly used depending on the units. We have 8.314 Pascal cubic meters per mole per Kelvin, or 0.0826 liter atmosphere per mole per Kelvin. So, the choice of the value of the universal gas constant would depend entirely on the units of the pressure, volume, and temperature being used. And finally, T is the absolute temperature of the gas. Notice that we are using absolute temperature, so these are your units of Kelvin and Rankine, and not relative temperature such as degrees Celsius and degrees Fahrenheit. So do not forget to convert your temperature to absolute units. Okay? Now let us illustrate how the experiment will proceed. In the Dumas method, your volatile sample is placed in an Erlenmeyer flask, which is sealed by an aluminum foil with a little hole at the middle. The purpose of the hole is that as we heat the flask and your sample vaporizes, some of the excess vapor of the sample would escape from the hole. The main idea is that after heating, you will be left with a flask that is filled with your gaseous sample, because we have heated your sample, and all of the excess gaseous sample would have already escaped from the hole, such that the pressure inside of your flask would be the same as the atmospheric pressure outside. Okay? And that gives us an avenue to determine the pressure inside the flask even though we are not directly measuring it, because we are only measuring the pressure of the atmosphere around. Now, after we have vaporized the sample, and then after the gaseous sample has completely occupied the inside of the flask, what we then do is we cool the sample, and then your flask would then contain your sample condensed at the bottom of the flask. Now, just to clarify, the sample at the beginning of the experiment and the sample at the end of the cooling are not equal. They do not contain equal quantities. For our initial sample in the experiment, we are required to place 5 ml of the unknown sample, but then after evaporating the sample and then subsequently condensing the sample by cooling, the amount of sample left in the flask will not reflect the initial 5 ml that you have placed. Instead, the amount of sample left in the flask will be the same amount of vapor that was in the flask during heating, such that if you know the mass of the sample left in the flask, you would also know the mass of the vapor inside the flask. And this is the sample mass that we need to calculate. Okay? So once we know the mass of the sample inside the flask, we then determine what is the volume of the flask. The total volume of the flask is measured by determining the volume of water that can be fit inside the flask, and that will be demonstrated later. So once we know the mass of the vapor, you also know the volume of the container. We can also measure the temperature of the sample during heating, and we will also be able to determine the pressure of the atmosphere, which is also equal to the pressure inside of the flask during heating. All of these parameters can then be placed into the ideal gas equation to determine the molecular weight of your substance. So how do we do it? The ideal gas law is PV equals nRT. And remember the definition of molecular weight. The molecular weight is equal to the mass of the substance over the number of moles contained in that substance. Such that if I rearrange the second equation, we get the number of moles is equal to mass over molecular weight. And if we substitute that to the ideal gas equation, you can see now how can we compute for the molecular weight of the substance. So our equation would then be PV equals mass over molecular weight times R times T. Solving for the molecular weight, we have mass of the sample times R times T over PV. This is now our equation for determining the molecular weight of our unknown substance. Okay, and with that, let's watch the demonstration. We start the experiment by cleaning the flask. Now, we want to start with a very clean and dry flask because impurities inside the flask would affect our data. After thoroughly cleaning the flask with soap and water, we then rinse the flask and then dry the flask in an oven. You want the flask to be very dry because even tiny amounts of water vapor inside of the flask would affect your determination of the molecular weight. So after drying of the flask, we then cool the flask such that it will be at room temperature before we use it. Okay, so here we are leaving the flask to cool before using. Next, we weigh the flask. We want to determine the mass of the empty flask. Now, we want to do that because we will be using that data later on to determine the mass of the sample inside of the flask. Okay? Now, do not record the mass of the flask given in this video because you will be given your own mass of the flask in our data sheet. Okay? After recording the mass of the flask, you see now that she is placing a sheet of aluminum foil at the top of the flask secured with a rubber band, and then we are weighing it again. We are interested on the mass of the flask plus the aluminum foil plus the rubber band because again we will be using that later to determine the mass of the remaining sample inside of your flask. Okay? And again, do not record the actual mass displayed here. You will be given the mass of the flask in the raw data. Okay, after recording, we are now ready to inject our unknown liquid. Now remember, in your experiment, it's your task to determine the molecular weight of the unknown liquid plus its possible identity. Okay, we will give you a clue, and the clue is that your unknown liquid is an alcohol. So after you have determined the molecular weight of this alcohol, you can then search for the molecular weights of the common alcohols, and then you can cross-reference to see what is the possible identity of your unknown liquid. Now she is injecting 5 ml of the sample inside the flask. Take note that she is doing that very carefully such that she will not introduce a very big hole in the aluminum foil. You want to have a hole in the aluminum foil to let some of the excess vapor get out, but you don't want the hole to be very big because you will be introducing significant amounts of air inside of your flask, which will affect our reading later. Okay, and then afterwards, we are now ready to place the clamp on the neck of the Erlenmeyer flask. The clamp allows us to suspend your Erlenmeyer flask into a boiling water bath. Basically, what we are trying to do is we want the flask to reach the temperature of the boiling water, and that would allow the unknown liquid to vaporize. After attaching the flask, you see that we are now boiling water in a beaker to which we are suspending our Erlenmeyer flask. Once the water is boiling, we are assuming here that the temperature of the boiling water is also equal to the temperature of the flask. It's also equal to the temperature of the vapor inside of the flask. And that gives us a measure of the temperature of the vapor. Okay? Once all of the liquid sample inside has been vaporized, we now remove the flask to allow the sample to cool. The cooling of the sample would allow the vapor inside to condense. And in here, we are measuring the temperature of the boiling water. we are not assuming that the temperature of the boiling water is 100 degrees Celsius because that 100 degrees Celsius boiling point is for normal atmospheric pressure. Okay? This is now our flask with the vapor inside. We are letting this cool first before we can weigh it, such that we can determine the mass of the remaining sample inside. Okay? So in here, we are weighing it. Remember earlier that we weighed the empty flask with the foil and the rubber band. Now we are weighing the flask, the foil, the rubber band, plus the sample inside, such that if we subtract the mass of the empty flask, the foil, and the rubber band from the mass containing the sample, what we get is the actual mass of the vapor inside. Okay? Before doing this, it's very important to make sure that there are no water droplets adhering on the outside of the flask. So the outside of the flask was wiped dry before attempting to weigh it. Now that we know the mass of the vapor inside, we also know the temperature because we measured it earlier. Now we will be determining the volume of the flask. So as I've mentioned earlier, we can determine the volume of the flask by filling it with water and then measuring the total volume of the water inside the flask. Because the total volume of the water inside of the flask would also be the total volume of the space inside the flask. Okay? So you see here that the Erlenmeyer flask is now full of water, and we are using a graduated cylinder to gradually measure the amount of water inside of the flask. The volume of the flask is given in your raw data. Okay, after measuring the volume of the flask, just a quick recap on the data that we have already gathered. We now have the mass of the vapor inside. We also have the temperature of the vapor inside during heating, which we measured earlier. We also have the volume of the flask, which would be the volume of the vapor. So the remaining thing to measure is the pressure of the vapor inside. I have mentioned that the pressure of the vapor inside would be equal to the atmospheric pressure because there was a hole in our foil. This is how we measure pressure. This is called a barometer. If you take a look at the black arm would be pointing to some numbers. The black numbers are in hundreds of Pascal and the red numbers are in millimeters of mercury. For our purpose, we need the value of the pressure in millimeters of mercury and then later convert it to atmosphere. And with that, this demonstration to the experiment is over. So please take a look at the uploaded raw data, consult with your group mates, and prepare your final reports. Thank you and always keep safe.